Good morning. Our discussion today will still be about Chapter 18, Gravitational Fields, and I will discuss some example problem related to gravitational potential. Problem number 1, define gravitational potential. Gravitational potential at a point is defined as the work done in bringing or moving unit mass from infinity to the point. Question B. Explain why values of gravitational potential near to an isolated mass are all negative. The potential at infinity is defined as being zero. The forces are always attractive, so work got out in moving to a point. So, in other words, work is done on the mass when moving it to infinity. Question C. The Earth may be assumed to be an isolated sphere of radius 6.4 times 10 to the 3 kilometer, and the mass is given, and an object is projected vertically from the surface of the Earth so that it reaches a certain altitude. Now, we want to find the change in gravitational potential for the object. And this is the answer. I will explain to you that we consider the Earth to be a sphere of radius r. R is 6.4 times 10 to the 3 kilometers. We should convert this into meter. So this will be 6.4 times 10 to the power of 6 meter. And then this is r. We project an object vertically from the surface of the Earth so that it reaches an altitude of 1.3 times 10 to the 4 kilometers. This also should be converted into meters, so it becomes 1.3 times 10 to the power of 7 meters. Now, this is h. Now, we know that the equation of gravitational potential is phi equals minus gm over r. The magnitude is gm over r. This is always negative. So when we want to find delta phi, it will be g times m times 1 over r1 minus 1 over r2. Yeah, r1 is this 6.4 times 10 to the 6. r2 is this altitude, but we have to calculate from the center of the Earth. So we have to add this by 6.4 times 10 to the power of 6 meters. So I have here the g, 6.67 times 10 to the minus 11, times mass of the Earth, 6 times 10 to the 24, and r1 is 6.4 times 10 to the 6, while r2 is this value, 1.3 times 10 to the power of 7 plus 6.4 times 10 to the power of 6 meters. So it is 1.94 times 10 to the 7 meter. Yeah, so we have the change in potential. It is 4.19 times 10 to the 7 joule per kilogram. In the next question, we want to find the speed of projection from the Earth's surface, assuming air resistance is negligible. Here, we can see that the kinetic energy of the object is converted to gravitational potential energy as the height of the object from the surface of the Earth increases. So we can say that kinetic energy at the surface of the Earth will be converted into potential energy, which is mass times the change in gravitational potential. So here, half mv squared equals mass times delta phi. We have already calculated delta phi before, so we can just use that value. That we can cross m out, so phi squared is equal to twice the delta phi, which is 8.38 times 10 to the 7. So phi is 9,150 meter per second. Question D suggests why the equation phi squared equals u squared plus 2as is not appropriate for the calculation in CII. It is because the acceleration is not constant. Question number 2. By reference to the definition of gravitational potential, explain why gravitational potential is a negative quantity. We have discussed this before, that gravitational potential at infinity is 0, and gravitational force is always attractive, so work is done as the object moves from infinity. It is the same as the previous question. Question B. There are two stars, A and B. They have their surfaces separated by a distance of 1.4 times 10 to the 12 meters, as illustrated in this figure 1.1. Point P lies on the line joining the centers of the two stars. Here is point P. The distance x of point P from the surface of star A may be varied. The variation with distance x of the gravitational potential phi at point P is shown in this figure 1.2. Now the question is, a rock of mass 180 kg moves along the line joining the centers of the two stars from star A towards star B, and we want to use the data from figure 1.2 to calculate the change in kinetic energy of the rock when it moves from the point where x equals 0.1 times 10 to the 12 meter to the point where x equals 1.2 times 10 to the 12 meter. State whether this change is an increase or a decrease. So we want to go back to this figure 1.2. When the x is 0.1 times 10 to the 12 meter, we have to see from the graph, 0.1 times 10 to the 12 is here. When x is at this point, then the phi, the gravitational potential, is minus 10 times 10 to the 8 joule per kilogram. And when x is 1.2 times 10 to the 12 meters, then when x is 1.2 times 10 to the 12 meters, then phi is minus 14 times 10 to the power of 8 joule per kilogram. In this situation, we have to realize that there is the change in kinetic energy when there is a change in potential energy. So there is a change in potential energy here from this point to that point, and we can find that delta phi. The delta phi is 14 minus 10 times 10 to the 8. We neglect the negative sign. And the mass is 180 kilograms, this one. So there is the change in kinetic energy, which is the same as the change in potential energy, which is 7.2 times 10 to the power of 10 joules. And if the PE is lost, then the kinetic energy is gained, and vice versa. In this case, the potential energy has been lost. So it means that kinetic energy has been gained. So initially at x equals 1.2 times 10 to the 12 meter, the phi is minus 14 times 10 to the 8. At x equals 0.1 times 10 to the 12 meters, the phi is minus 10 times 10 to the 8 joule per kilogram. So delta phi is the final minus the initial phi. So in this case, we have the increase in kinetic energy because PE is lost. The next question is, we want to find the minimum speed v. V is the speed of the rock at a point where x equals 0.1 times 10 to the 12 meters. We want to find that minimum speed v such that the rock reaches the point where x equals 1.2 times 10 to the 12 meters. In this case, the rock needs to reach only the point where the field is 0, the gravitational field is 0. In the graph, this is where the change in the gravitational potential is 0. And here is the value of phi, where the gravitational potential change is 0. Here is the value, and the value is minus 4.4 times 10 to the power of 8 joule per kilogram. The rock needs only to reach this point, and afterwards the rock would be attracted by the field of another planet. So the calculation will be like this. The energy required is 180, the mass, multiplied by the delta phi. The delta phi is 10 minus 4.4 times 10 to the power of 8. Yeah, this is the energy. Or if you want to calculate the energy per unit mass, we don't have to include the mass. And later, delta kinetic energy should be equal to the delta of GPE, gravitational potential energy. Yeah, you can cross M out, so you get V, which is equal to 3.3 times 10 to the 4 meter per second. Okay, now please do your assignment. I have uploaded some questions and you can answer the questions given. Only number 10, 11 and 12 because number 9 has been discussed. And then scan your work and submit it by uploading it to Scholar. If you have any question, you can contact me at this number. Okay, thank you. I hope this video is useful.